Hi, in this video, we will discuss the basic differentiation and integration rule. These are the basic integration rule function and also the formula that you need to master. Let's apply differentiation and integration to each function one by one. So for the polynomial function, if you differentiate x, you should get equal to the constant 1. And if you differentiate any x to the power of n plus 1 divided by a constant n plus 1, we should get equal to x to the power of n. And in this case, the n cannot be equal to -1. The tip to master the integration formula is to understand its derivation, because the integral is just the reverse of the derivative. So most of the students may not familiar with the derivative of basic trigonometric function and its inverse, and we will cover that later. So in this case, if you integrate 1 with respect to x, you should get the answer in x plus c. Let's say you have integrate x to the power of n. Let's say your n is equal to 5. You should get x to the power of 5 plus 1, which is 6, divided by 6 below. So this is your answer. And don't forget the constant. So if let's say your n is equal to -1, then this formula cannot be applied. Okay, let's move to the exponential function. When you differentiate exponential function ex, you should get equal to ex. And normally, the general formula is you have to multiply ln e, which is e is the base. Ln e gives you 1, therefore the answer is in ex. So by using the same approach, let's say you differentiate ax over ln x, a. So you should get the original formula ax over ln a, and you have to multiply with ln a. Therefore, these two things can be cancelled and you get the ax in this case. So you should be careful that when you have some function like y equal to ex, so you can see in the red color, this is the graph. And if you have a function y equal to 2 to the power of x, this is also exponential function as well. So we call it as an exponential function with base 2. In this case, since the exponential has 2 point something, therefore the rate for y equal to 2x is much lower. If you have a base equal to 10 in this case, then the rate will be much faster. So if you have exponential function with base 1 over 2, you have something like this. This is because if you change 1 over 2 into this form, you will find that the rate is decaying. Where you have negative means it's decaying, and then if you have positive, it's growing. Next, we have a ln function here. What is the derivative of ln x? You should be able to get 1 over x, and if you integrate 1 over x, you should get equal to ln x plus c. So you should know that the ln x actually is the inverse function for the exponential function. For example, let's say you have a y equal to e to the power of x here. So you inverse it, basically you get your ln y equal to x. That's why we say the log is equal to the inverse function for the exponential function. Let's look at the basic trigonometric function. So if you differentiate sine, you should be able to get cos. If you differentiate tangent, you should get secant square. If you differentiate secant, you get secant. Well, if you differentiate the cos, you can see that sine, you get negative cos, and for the cos, you get sine. Right? There is a relationship there. So tangent becomes negative cotangent. secant square becomes cosecant square. Secant become negative cosecant. Sec becomes cosecant, and tangent becomes cotangent. So you can see that there's a relationship where positive change to negative, while sine change to cos, cotangent change to tangent, and cosecant change to secant. So we can use this relationship to memorize the formula. So if you reverse the derivative, you can get the integral answer here. So I think you are familiar with cos and sine function. However, if you see function like this, you should be able to directly give me the answer. So integrate the secant square, you get tangent. Okay, integrate the secant, you get secant. Well, cosecant square, you get negative cotangent. As I say, positive become negative, tangent become cotangent. So these are 4 additional integrations where you must familiar. Instead of memorize the formula, you can refer to appendix 1.3 for the derivation. So we say that if you differentiate tangent, you get secant square. So these are the 2 formula we use to derive. Firstly, so tangent is equal to sine over cos. So if you apply the quotient rule, so quotient rule say that for the v, you remain here, and then you differentiate du over dx. So same approach, cos x will remain here, and then we differentiate the one at the top, which is the sine x, and then minus with u is here, and then multiply with dv dx. So same, minus with the one at the top, okay, and then differentiate the one at the bottom. And then when we divide with v square, which is the one at the bottom, so we differentiate with cos x of 2. Differentiate sine, you get cos for this term. So cos multiply cos, you should get cos square. So differentiate cos, you get negative sine. Negative sine multiply negative sine here, you get positive sine square here. By using this identity, we are able to reduce it equal to 1 over cos square x. So since 1 over cos x is secant, then we can write the answer in secant square. So same method can be applied to derive the cotangent to negative cosecant square. So you can see firstly cotangent is 1 over tangent, and then is equal to cos over sine, and then we apply the quotient rule, we get this. So after you differentiate, you get something like this, and apply the identity, this thing equal to 1, so you get something like negative 1 over sine x of 2. So 1 over sine is cosecant, therefore you get this final answer. So we say that if you differentiate the secant, you get the secant tangent, and if you differentiate the cosecant, you get the negative cosecant cotangent. So we can use the similar method for the derivation. So you can see that we apply the quotient rule here, and then so differentiate 1, you get 0, so this term missing, okay, will be eliminate. This term also the same, therefore you get negative d over dx cos x, you get the sine part, and differentiate sine x, you get the cos part. So expand this term, we get sine over cos, and multiply with 1 over cos. And 1 over cos is secant, sine over cos is tangent. And lastly, you have negative there, 1 over sine is cosecant, cos over sine is 1 over tangent, which is cotangent. So please take note that if you can remember this formula, you can use the relationship to form this answer. For example, secant, you know, there is a relationship with cosecant. So secant relationship with cosecant. So positive become negative, and then lastly the tangent has relationship with cotangent. So you can use this relationship to form the answer. Let's continue with the inverse function of trigonometric function, which is this three terms. So these are the inverse function for sine, tangent, and secant. If we differentiate the inverse function for sine, you get something in polynomial function. You can see there's a 1 minus x squared polynomial function in the square root. And if you differentiate the arctangent x, you will get 1 over 1 plus x squared. If you differentiate the arcsecant x, equal to 1 over x multiplied with square root x squared minus 1. So please take note that if you have something like this, there's a triangle, so with some length AB and your R, so you should notice that A squared plus B squared should be equal to R squared, where in this case 1 minus x squared, you can assume that A squared plus B squared. Here also the same, you see the pattern, A squared plus B squared. And lastly, this one, x squared plus b squared, something like that. Okay, so this has something to do with trigo substitution. We will discuss this later. If you integrate this function, you should get back the inverse function for sine. Okay, integrate this, you get inverse function for tangent, arctangent. And if you integrate this, you get the inverse function for secant. To find the differentiation of the inverse function sine x, to get this answer, we must use the inverse function rule. So this is the inverse function rule. dy over dx is actually equal to 1 over dx over dy. And also the same, we need some identity. So in this case, to find the dy dx, let the y equal to arc sine x. So if we inverse this function, we get the x equal to sine y. So to differentiate dx over dy will be much more easy. So we get the dx over dy equal to cos y. And to transform the cos y into the x format, we need the identity formula, where your cos y should be equal to square root of 1 minus sine square y. Right, you substitute the answer, you get this. Since the x equal to sine y, we can replace the sine square y to be x squared. Thereby, we can substitute this answer into the original inverse function rule. Thereby, we get this. And this is the answer for the differentiation. By using similar approach, where you can see you want to take the differentiation for cos inversion of cos x, without solving the problem, you can use the relationship cos you get sine, sine you get cos. So positive get negative, right? So the answer remains. So let's look at the derivation for this. So in this case, to find the dy over dx, it will be very difficult because your y is arc cos x. So let the y equal to arc cos x, and when we inverse it, you get the x equal to cos y. Take the dx over dy, you get negative sine y. Similar approach, to get the sine y, it will be just equal to square root 1 minus cos square y, where you can substitute inside. And since your x equal to cos y, you can replace the x here, you get x squared. And this is your dx over dy. Thereby you can substitute inside this formula 1 over dx over dy, and this is your final answer. So please beware that this is the inverse function, inverse sine function is not equal to the reciprocal function here. And this reciprocal function can be equal to this format, which is sine function to the power of -1. And for sine to the power of 2 here is equal to the sine function to the power of 2 here. And if you have power of 3, power of 4 and so on, this will change as well. So for any inverse function, you can use this inverse function rule to solve it. Okay, if you want to differentiate, let's say inverse function for tangent, to get this answer, we have to use the trigonometric identity for tangent and secant here. So in this case, we let the y equal to arctangent x, and your x is equal to tangent y. Dx over dy will be secant square, we call it. And then secant square y, from this formula, will be just equal to 1 plus tangent square y. Okay, we substitute using the identity. And then since your tangent y is equal to x, then we can get this answer. So this is your dx over dy. We substitute inside this rule, we get back the dy over dx, which is the answer. So the same method can be used to differentiate the inverse function for secant. So to get this answer, firstly, let the y equal to arcsecant x. Then we get the x equal to secant. So we take the dx over dy, we get the secant. And then by using the identity, your tangent y should be equal to square root 1 minus, it should be secant square y minus with 1. So we substitute inside this formula, we get this term. So in this way, we can substitute the x inside it, we get x here. So secant square y, we get x squared here. And we have to substitute the dx over dy into this formula. So we have 1 over dx over dy. Therefore, we get the final answer to be this. Same approach can be used to differentiate the inverse function for cosecant and inverse function for cotangent, where the trigonometric that we need, since this one is a cotangent and cosecant, so we have to use this identity. Okay, so since the steps are almost the same, you can refer to this for the derivation. So far, we have able to prove this. So you can see that if you differentiate the sine, you get this answer. However, if you differentiate the inverse function for cos, you get similar answer but in negative. So we can say that this result is redundant. It's like repeated. So similarly, if you differentiate the inverse function for tangent and secant, then you get similar result but in negative. Why do we care with all of these inverse stuff? So let's say you want to inverse something like this. So it will be very difficult for solve this problem. However, now if you integrate both sides, then this can be cancelled, but you will find that if you integrate something in square root 1 minus x squared, you get the result in inverse function for sine. And if you integrate something in a squared plus x squared, then you get the result in inverse function of tangent. So this is similar to the case that we have here. And we can assume that your x is equal to a constant a multiplied with a tangent x. And this is what we call the trigonometric substitution. So there are some typo here. This should be, this means the arc, okay, is not the constant a, but this is the constant a, okay, which I should put here to be the inverse function. So instead of having this, actually we have a redundant information here, where 1 plus x squared related to something in cotangent as well. So we can actually let the x equal to constant a multiplied with cotangent x to be our substitution. This should be angle. Okay, this should be angle. However, since these are redundant, so normally we do not use this. Okay, we just use the substitution on the left hand side, which is sine, tangent, and secant. So we move back and we have a last part, which is the integration for basic trigonometric function. So let's say for the first two cases we have discussed before, which is the sine and cos. However, if you want to integrate tangent, cotangent, secant, and cosecant, you get something in ln. So how to get this? So to know why integrate the tangent, you get something in ln. Okay, we can refer to appendix 3.1 for the derivation. So what we need is some trigonometric identity, and using the integration technique by substitution. So you know the tangent is sine over cos and cotangent is cos over sine. Thereby we can substitute inside the formula. Okay, tangent we get sine over cos, and you see that if you differentiate the cos, you get the sine. So there are relationships where we can use the substitution. We let the t equal to cos x dt over dx, then you get the negative sine x. So sine x will be the negative dt over dx from here. And then you can substitute your t to the cos x here. Dx can be cancelled. Dx over dx here become 1. Then you get this result. And when you integrate negative 1 over t, basically you get negative ln t. So this is the final result. However, if you integrate the function in x, we expect you to give the answer in x as well. So you have to do back substitution. So since we know the t is equal to cos x, we can substitute inside and we get back our result in x. So this is the final answer. So we can use the same approach to integrate the cotangent x. So cotangent x is 1 over tangent. 1 over tangent is cos x over sine x. So if you differentiate sine, you get cos. Therefore, we can use the substitution method. We let the t equal to sine x here. You take the dt over dx, you get the cos x here. So we get this answer. And then dx can be cancelled off, you get the dt over t, and then 1 over t integrate, you get ln. Next, you do the back substitution, substitute the t inside, this is your final answer. So same thing, basically if you understand, you can remember this formula, you can use the relationship to get this answer also without doing the derivation. So tangent has something to do with cotangent. So negative becomes positive here, and then cos becomes sine. So you can use this relationship. So if you integrate the secant, you get ln secant plus tangent. So how can we get this? So first of all, you must know that if you differentiate the tangent, you get secant square. If you differentiate the secant, you get sectan. This means that you can integrate the secant square and secant. So we are trying to make the original formula secant into secant square and secant. Thereby, we multiply it with secant x plus tangent x. We have to divide secant x plus tangent x so that this becomes 1. Okay, so we multiply inside, we get this formula. So same approach for the to integrate the cosecant. Okay, where we know integrate cosecant square, we get negative cotangent, and you know integrate the cosecant x, cotangent x, you get this answer. Thereby, we try to multiply this to get cosecant x square, and then cosecant x, cotangent x here. Okay, where you can use the integration to solve later. So from this integration, you can see that if you let t equal to secant x plus tangent x, you differentiate it, secant you get secant, tangent you get secant square. Where there is a relationship, you can use the substitution method. So we let the t to the bottom part, and then dt or dx, you found this to be the upper part. Okay, we substitute, and then you can solve this easily. 1 over t, you integrate, you get ln, and then back substitute your t, you get the final answer. So similar approach on the right hand side as well. Okay, so you get this result. So these are the summary for what we have so far. So if you differentiate sine, tangent, secant, you get this answer. On the other hand, if you differentiate cos, cotangent, cosecant, you get this answer. If you integrate sine, tangent, secant again, okay, you get this answer. And if you integrate the cos, cotangent, and cosecant, you get this answer. Okay, so I would like to share with you that for this part, you can see the information is redundant, where we can use this relationship for the ease of your memorization. So let's say you memorize the left hand side. Okay, first relationship, positive become negative, where you can see that on this left hand side you get all positive, on the right hand side here is all negative, right? If the negative is here, then you get positive on the other hand. So you can use this relationship. Next thing, okay, sine become cos and cos become sine, where sine here become cos. So sine here, let's say you differentiate cos now, it becomes sine, right? So it's a reverse thing. So tangent become cotangent, secant become cosecant. Okay, so with this relationship, it's helpful for you to remember the basic derivative and integral formula. So you should have more idea, okay, about the basic integration rule. So now let's try some example. Let's k to be the constant equal to 5. Let's say you have a function in u, which is this. So try to find the integration for this problem. So on your right hand side, this is the technique that you can apply. So first technique, expand. Okay, you can expand this. You get 15, 5u multiply 5 multiply 2, you get 10u squared. Next technique you can apply is the sum rule, where this one is inside the integral. You can separate it, okay, separately. So by using the same approach, we separate the term. So for the scalar multiplication rule, if k is a constant, then you can take out the constant. So in this case 15, 5, 10 all are constant, therefore it can be taken out. So we can apply the basic integration rule for the polynomial. In this case it's a constant 1. In this case it's a u to the power of n. Okay, so this is polynomial function. So let's say you have 1 here. If you integrate, you get u. Okay, and don't forget the constant, and then you differentiate. You integrate the u, you get u squared over 2 plus a constant, and then u square. Okay, you integrate, you should get u to the power of 3. So there is a typo here. This should be u to the power of 3. Lastly, we can combine all the constants c1, c2, c3 into just a c here. Okay, so if you have familiar with this technique, you should be able to do it faster. So for example, this step can be skipped. Okay, where you can directly from here you can get this answer. Next, let us look at rational function like this one. So by applying the expand, sum rule, and scalar multiplication rule like previous one, we are able to obtain this answer. Okay, you multiply 5 inside, you get this, and then you separate it, and then all the constant can be taken out, right? Like this one. So for the second integral here, you can see that if you differentiate u squared plus 3, you get 2u. So this one 2u here, and then you can take the 5 out. So this is something relevant to ln function, where previously if you integrate 1 over u, you get ln u. Okay, so if you integrate some denominator, okay, at the top is the derivative of your denominator, so your answer should be in ln, okay, b. So using the same approach, if I differentiate u squared plus 3, I get 2u. Okay, so my answer should be in this form, ln u squared plus 3. 1 over u, I integrate, I get this answer. Okay, u to the power of negative 3, I can use normal polynomial function. Okay, u negative 3 plus 1 divided by negative 3 plus 1. And then lastly, okay, this one remains. And then I simplify this, I get the final answer. Let us continue to integrate the exponential function. So we can multiply inside, we get this, and then we can separate the function to make it easy for you to view. The constant can be taken out. So based on the basic integration rule, if you integrate EU, you get EU here. So in general, this should be divided by ln E, where your ln is equal to 1. So if you have a to the power of u, okay, if you integrate, you get 1 over ln a. So a is the base. So by using same approach, so if you have EU here, okay, EU ln e, you get 1 here. So if you have 2u here, so 2u you have divided by ln 2, which is the 2 is the base. However, if you have negative 0.5 here, okay, you cannot do this because based on this formula, your a must be greater than 0. Okay, so we cannot do that. And these two items, we can find the answer by using this formula, but your a should be always greater than 0. So if you compute this term, this is undefined. So let's say we have integration instead of having negative, we have a positive 0.5. So since a greater than 0 in this case, so we can solve it using the previous method where we divide by ln the base is 0.5. So we can get the answer. So you can also use another approach. Okay, this is a longer step, but in the end you should get the same answer as well. Okay, let's continue with the basic trigonometric function like the cos and sine. Okay, so if you integrate cos, you should get sine. Okay, how about this? So we can actually use the trigonometric identity where this multiplication term can be simplified into sine function only. Okay, so your A is 5u, your B is 7u. So here 7 plus 5 you get 12. Okay, 5 minus 7 you get negative 2u here. So with that you're able to obtain this function. So basically on the left, cos, okay, so basically cos, you integrate, you get sine 5u divided by, you differentiate 5u inside, you get 5 at the bottom. Okay, let's continue with this. So 1 over 2 you remain, and okay, sine, you integrate, you get negative cos. Okay, sine, you integrate, you get negative cos here also. And you have to differentiate 12u inside, you get 12, okay, you have to divide it. So you differentiate negative 2u, okay, you get negative 2. Where this is the general formula for the sine and cos. As you can see, the constant a remains here. So sine becomes negative cos, cos becomes sine. You integrate with respect to u. So b is your constant. So bu, if you differentiate bu, you get the b here. It has to be divided. Okay, bu here. After that, you get divided by b. So let us continue with the inverse function for the sine x and exponential function. So this is a new rule that you need to know. So inverse function rule is given by this formula. So in simple, you can look at this graph where the function y is equal to an inverse function, and if you integrate the inverse function with respect to x, actually what you obtain is area 2. So the total area is x multiply y. So this is your total area xy, and if you're able to find the area 1, okay, which is you integrate the y function with respect to 1, then you can find the inverse function. So this is the technique that we use. So in this case, let's say you want to solve, okay, you want to integrate the inverse function for cos, integrate the inverse function for ln x. Okay, any inverse function, if you want to integrate, we can use the inverse function rule. So for the first case, let's solve the inverse function for the cos. Okay, we let the y equal to inverse function cos, and this is our inverse function. And reverse it, we get our x equal to cos y, and this is our function in y. So to integrate the cos y is very difficult, we don't know the answer. So therefore, we can solve using the right hand side. The right hand side is the total area minus with the area 1, and this is your area 1. Okay, integrate the function 1, which is cos y. So you can substitute your y inside, okay, you get this, and then you integrate the cos y, you get sin y. By using the identity, sin y is equal to this, and then we can substitute the y inside, right? Okay, so you substitute the y here, you get this. So cos multiply inverse cos This term can be cancelled off. You get the cos only. So this is your final answer. So by using the same approach, we can solve for the ln x. So you want to integrate this. We don't know the answer, but you know that this is inverse function for exponential. Thereby we can use this formula to solve it. So let your y to be ln x. So this is the inverse function in x. And then we reverse it. Okay, we inverse it. And then we get back the x function equal to exponential to the power of y. This is in y function. So we substitute this inside this formula. So you get the area 1 to be this, and then xy to be the total area. Substitute your y inside, you get this, and then ey, if you integrate it, you get back ey as well, and don't forget your constant. So you know that x is equal to ey, you can substitute. Therefore, you can get the final answer. And lastly, we combine these two answers. Okay, we get the total solution. With that, we have covered the basic differentiation and integration rule. So these are some techniques that we use, okay, to fit the integrand to the basic integration rule. So the technique that we have shown you just now, so far is the trigonometric identity. So you should master all of this. And then let's say expand, okay, you should know this well as well. Separate the numerator, okay, you should know how to separate this, right? I think this is quite basic. So completing the square, okay, so the term here, can you make it into the format of completing the square? Okay, so this one later I will show you more, maybe. Forget to mention that for the expand case, okay, so for the power of 2, we can choose this. So where you can see the coefficient is 1, 2, 1. If the coefficient, the power is the power of 3, then you can have this coefficient 1, 3, 3, 1. Okay, so completing the square. So in future we will show you more. Okay, this is very useful. Dividing the improper rational function, where you can see this rational function can be further reduced. Okay, how to reduce it, you will learn later. Add and subtract term in the numerator. So for example, you want to integrate this function. So it's quite difficult, but if you look at this, okay, we want to differentiate x squared plus 2x plus 1, you get 2x plus 2. So plus 2 here, right? Then we can get the answer in ln. So to solve this, okay, we have to, instead of adding the plus 2 term here, we have to minus 2 back. Okay, so we can separate it out. So this term you can get the ln, and another term, okay, you remain it to be 2. So x squared plus 2x plus 1 is equal to x plus 1 squared as well. This can be found from completing the square. Then you can see that this is in ln to the x squared plus 2x plus 1 here, sorry, okay. So you can see the ln to the this term, okay, put everything here. So if I take the integration, okay, I should get this. And for this term, we can use the substitution, let t equal to x plus 1, and then you take the dt over dx, you get dt equal to dx. So substitute inside, you can solve it easily if you take the integration for this part also. Lastly, okay, you have trigonometric identity, okay, which you have learned so far. And then if you have some function like this, okay, you want to convert it into this form, a much simpler form, like this one, where if you want to integrate secant square, you can do that. Okay, so if you integrate this, then you will get tangent x, and for this term, sine over cos is tangent, and 1 over cos is secant. So basically, the answer to integrate this, you should get the secant, right? So, if you integrate some function here, like this is very complicated, okay? So you can choose multiply the conjugate, and then after you multiply the conjugate, you should be able to get into this form. 1 minus sine square x can be substituted by using the identity. In this case, you can simplify 1 over cos, you get secant square x, sine over cos square x, you get the tangent secant. Okay, we will discuss more later.